All right, so suppose that the absence of enzyme, so this doesn't have a catalyst, right? It's the one without the enzyme. The forward constant, this is a rate constant. Notice the small k, meaning it's for a reaction going in one direction, right? And this would be how many times per second or minute, in this case per second, this reaction would go, right? This is that chapter with the rate constants in general chemistry, if you're curious. This is the kinetics one, rate constant. Okay. Anyways, that's forward reaction. That's why it has an F. For the conversion going from S to P, substrate to product, it happens 10 to the negative 4 times per second. Notice in this case, because it's directly in S to P, it's actually literally like S has disappeared 10 to the negative 4 times per second. Okay? So many of these biochemistry reactions are very simple if you look at them as rate reactions. You still have like one reactant, right? All right. The reverse rate constant, which is K sub R, notice again it's a lowercase k. For the conversion going from P to S, so product to substrate, is 10 to the negative 6 times per second, right? Again, note that we're looking at going one direction to the other in each case. Okay, so there's two things we need to get from here. We need to get a K and then a delta G naught prime. Delta G naught prime is always going to be a standard free energy. That's the delta G part. Standard is the naught, by the way. Delta G would be the free energy part. And then this being at pH 7, which is a typical biology related pH, is the prime. That's the modifier. Okay? If it didn't have a prime, this would not be a pH 7. That would not be a thing. Again, it's really on catalyzed reaction. Okay, so the first part you do is you need to get a K, right? And some of you had me for general chemistry, and I make a big deal out of this. Ks, capital Ks, are combinations of small k's. Okay? So whenever you see a capital K, it's always, well, first off, equilibrium constants are always products of reactants, right? Okay? And so you're looking at producing products, right? When you're looking at this. The second thing is a capital K is always a combined or combination of small k's. If you have a reaction going in one direction, it's going to have to be over a reaction going in the opposite direction if you're in equilibrium, right? That's going to determine the equilibrium balance. Remember that the equilibrium, what's equal? How fast these reactions are going, right? Okay. Okay, to counteract, how fast, I need water. How fast these reactions are naturally go, we'll have to build up some product, won't we? Okay? So the easy way to do this is to take your K's here, and you take your K forward divided by a K reverse. And that will give you your capital K. Notice that that's the difference between those, right? 10 to the negative 4th is 100 times larger than 10 to the negative 6th. So capital K is 100. What does that actually mean? Well, to counteract the fact that this one goes so much faster than the backwards reaction, you need 100 times the product as you have substrate. Does that make sense? Does that kind of help you so you don't have to memorize everything? Hopefully. Okay, so the next part we have to do is we have to calculate a delta G, don't we? Uh-oh, how do we calculate a delta G? Yeah, we need to do a Gibbs free energy. Is it related in any way to a equilibrium constant? Yeah, by that certain formula right there, isn't it? You remember that formula? So your delta G always equals negative R times T times the natural log of your K, your equilibrium constant, right? Okay. All right, so in this case, because we're doing a delta G naught prime, well, our delta G naught would normally be what's in here. But the prime means that we have to have a K prime for this, okay? Now, luckily, we have this in a biological situation anyways, so that makes this a little bit easier, okay? So what we're going to do here is we're going to take our R value. Don't forget it's the one in energy units. Okay, it's not the one in, gas terms. We'll put that in there. Next, we'll have our temperature. Well, what's the temperature of the typical standard temperature? 298 Kelvin, right? So we put that in there. No, in this case, it's 298. It's room temperature.
Well, what is 273?
Oh, that's absolute zero. Well, that's 0 degrees Celsius, yes. And that actually is the STP. That is the actual standard temperature, by the way, in case you're curious. Okay? Yeah. The lab conditions, standard lab conditions, is 1 atmosphere and an ice water bath, which is 0 degrees Celsius, right? Or 273 Kelvin. Because, as you notice, this room is much colder than normal room.
Oh, yeah.
And like our labs are actually like 19, 20 degrees recently. Like Dr. Evans had just done some experiments where they had to measure the lab temperature water, and it came out as a 19, 20 degrees Celsius, not 25. It was much colder. So, anyways, then we have our K, which we came up with just a little bit ago, right? So we plug those in. We get our final answer here. Ta-da! And we're done. Okay. Okay. Anybody have any questions about that part so far? No? Okay. So now we need to go to the next part. Suppose an enzyme enhances the rate of the reaction 100-fold. What are the Kf, Kr values for the enzyme catalyzed reaction? So let me ask you a question real quick. Enzyme catalyzed reactions. What does an enzyme or catalyst do? They're the same thing, right? Speeds up the reaction, but does it speed up one side of it? Or does it speed up the whole thing? Both directions? Both, exactly. All catalysts always speed up the reaction in both directions, right? Because they cut down that activation energy, meaning it's a smaller hill to go overcome both ways, right? Fantastic. So when you do this, it's a 100-fold increase. That means you just multiply both of them by 100-fold, right? Yeah. See that? And so does it affect your equilibrium? If you do the same thing to the top and bottom, what happens? It's the same. Yeah, your equilibrium stays the same, doesn't it? Again, this is actually the difference between kinetics, the speed of the reaction, right, and thermodynamics. What you end up with more of, right? So like equilibrium is how much of the product you end up at equilibrium, right? The product versus reactant, you end up at equilibrium. Delta G tells you the equilibrium positions, right? It tells you how much energy you, in this case, lose for making your product, right? It's thermodynamics. Or if you want to visualize this as the, remember the energy graphs we used to talk about where they have reactants over here, and it overcomes a hill, activation energy, and then a product. Yeah, there is, exactly. And this is all based on that, right? So for example, this stuff up here is the hill, isn't it? It's based on that activation energy. It's the speed, right? This stuff down here, it's the reactant versus product positions, right? Has nothing to do with the hill, the activation energy. Does that make sense? Anybody have any questions about this, or does that clear that up? No. So the enzyme catalysts never affect delta G's, never affect equilibriums, no effect. Okay? Only ever affect the speed, and they always have to affect the forward and the reverse reaction the same. Make sense? Which, the fact that they affect them the same is why it never affects this, right? Because mathematically, if you do the same thing at top and bottom, it cancels. Yeah. Okay. I'm going to stop on that. I think I'm beating a dead horse at this.